Hello everyone and welcome. Today we're going to deep into one of the most important topics in modern AI, how large language models actually learn language and how they are trained. If you have ever used ChatGPT, Claude or any AI assistant and wondered how does this thing actually work under the hood, so this video is for you. We're going to demystify the entire process. Over the next half an hour, we'll cover what language modeling actually means, how text is turned into something a model can understand, the architecture that powers modern LLMs, the full training pipeline from raw data to a helpful assistant, pre-training, fine-tuning and alignment, the challenges and costs involved, and where this technology is heading. I'll keep things clear and intuitive, building up from the fundamentals. You don't need a PhD to follow along. You just need some curiosity. Let's get started. What is language modeling? At its heart, a language model is a system that assigns probabilities to sequences of words. More practically, it's a model that predicts the next word given the words that came before. That's it. That's the fundamental task. Predict what comes next. Consider the sentence, the cat sat on dash. Your brain immediately suggests mat, floor, chair, and probably not, democracy, or something else. A language model does the same thing, but mathematically. It assigns a probability to every possible next word and picks based on those probabilities. Here is the profound insight. To predict the next word really well, a model has to learn an enormous amount about the world. To complete the capital of France is dash, it needs facts. Let's take some other example. To complete, she opened the door and dash. It needs to understand narrative and cause and effect. To complete 2 plus 2 equals dash, it needs arithmetic. To complete a line of code, it needs programming knowledge. So, this seemingly simple objective, next word prediction, forces the model to learn grammar, facts, reasoning, and even some common sense. All of that knowledge is implicitly captured in the statistics of language. Modern LLMs are autoregressive. They generate text one token at a time. Each predicted word becomes part of the input for predicting the next word. It's like a sophisticated autocomplete. Start with a prompt, predict the next token, append it, predict the next token, repeat it until it's done. This loop, powered by a massive neural network, is how these models write essays, answer questions, and hold conversations. Now, let's understand the pieces that make it work. Tokenization, turning text into numbers. Neural networks don't understand words, they understand numbers. So, the first step in any LLM is converting text into numbers through a process called tokenization. A token is a chunk of text, it might be a whole word, part of a word, or even a single character. Modern LLMs typically use subword tokenization, where common words are single tokens and rarer words are broken into pieces. For example, cat might be one token. Unbelievable might split into UN, BLE, BLIV, and so on. A space and punctuation are often part of tokens too. As a rough rule of thumb, one token is about 3 to 4 characters of English text or roughly 3 quarters of a word. Why not just use whole words? Two problems. Vocabulary would be enormous, millions of words, names, and variations. The model couldn't handle words it never saw before. Subword tokenization solved this. With a vocabulary of, say, 50,000 to 100,000, the model can represent virtually any text by combining subword pieces, including new or rare words. Algorithms like byte pair encoding or BPE build this vocabulary by finding the most common character sequences in the training data. The pipeline works like this. Text is split into tokens. Each token maps to a unique integer ID from the vocabulary. Each ID is converted into a vector, a list of numbers through an embedding. What is embedding? The last step is crucial. Embedding is a dense vector, maybe hundreds or thousands of numbers long, that represents a token's meaning. Remarkably, the model learns these embeddings during training such that Similar words end up with similar vectors. King and queen land near to each other. Happy and joyful are close. The model learns to place meaning into geometric space. So, by the end of tokenization and embedding, our text has become a sequence of meaningful numerical vectors, exactly what the neural network needs. Now, what is a network? So, we need to get into the transformer architecture now. The transformer architecture. The engine behind virtually every modern LLM is the transformer architecture. It was introduced in 2017 in a paper famously titled Attention is All You Need. Let's understand why it was such a breakthrough. Before transformers, language models used recurrent neural networks (RNNs), which process text one word at a time. In order, this had two big problems. They were slow, you could not parallelize sequential processing. They struggled with long range dependencies. By the end of long sentence, they had forgotten the beginning. The transformer superpower is the attention mechanism. Attention lets the model look at all the words in the input simultaneously and decide which ones are relevant to each other. Consider the animal didn't cross the street because it was too tired. So, what does it refer to? The animal, not the street. Attention lets the model connect it to animal by computing relevant scores between every pair of words. How attention works: for each word, the model asks, which other word should I pay attention to in order to understand this one? It computes attention scores, weights that determines how much each word influences the representation of every other word. This happens through what are called queries, keys, and values. Think of it like lookup system. Each word sends out a query asking for relevant information. Every word offers a key advertising what it has and where queries or keys match well. The corresponding values flow through. This is called self attention. Multi headed attention. Transformers use multi head attention, running many attention operations in parallel. Each head can focus on different types of relationships. One may track grammatical structure, another might track subject object relationships, another long range topic connections. Together, they build a rich understanding. The full architecture is a transformer stacks many layers, each containing a multi head attention mechanism, a feed forward neural network, normalization and residual connections that help training stability. Modern LLMs stack dozens to over 100 of these layers. Data flows up through the layers, and at each level, the model builds increasingly abstract representation from surface patterns to deep meaning. Crucially, unlike RNNs, transformers process all tokens at once during training. This parallelism is what makes it feasible to train on enormous datasets using modern GPUs and TPUs. This architecture efficiency is a big reason LLM could scale to the sizes we see today. Position information. One catch: since attention looks at all the words simultaneously, the model needs a way to know word order. This is added through positional encodings, signals that tell the line model where each token sits in the sequence. Without them, dog bites man and man bites dog would look identical. That's the architecture. Now, let's talk about how we actually train it. Pre-training, learning from the internet. Now, we reach the heart of it: training. The first and foremost resource intensive phase is called pre-training. This is where the model learns language and knowledge from massive amounts of text. Pre-training uses enormous text datasets. We are talking hundreds of billions to trillions of tokens. Sources include web pages, books and literature, Wikipedia and reference manual, code repositories, academic papers, forums, and discussions. The scale is staggering, far more text than any human could read in thousands of lifetimes. But it's not just about quantity. Data quality is critical. Teams spend enormous effort filtering out spam, duplicates, and low quality content, removing harmful or toxic material, deduplicating so the model doesn't over memorize repeated text, balancing different domains and languages. The saying garbage in, garbage out absolutely applies. Better data produces better models, sometimes more than just adding raw size. What's the training objective? The pre training objective is beautifully simple: predict the next token. The process: take a chunk of text from the dataset, feed it to the model. At each position, the model predicts the next token. Compare predictions to the actual next tokens. Calculate the error, the loss, adjust the model's parameters to reduce that error. How learning happens? This adjustment based step uses two key techniques. Backpropagation calculates how each of the model's parameters contributed to the error, propagating the error signal backward through the network. Gradient descent nudges each parameter slightly in the direction that reduces the error. Model has billions of parameters. The adjustable weights in the network. Each tiny adjustment improves prediction just a little. Repeat this billions of times over dataset and the model gradually becomes extraordinarily good at predicting text, and in the process learns grammar, facts, and reasoning. When you hear a model has 70 billion parameters, those parameters are the weights being tuned. Generally, more parameters mean more capacity to learn, though as well we see data and training quality matter just as much. So what is the cost associated to it? Pre-training a frontier model is one of the most expensive computational tasks humanity performs. Thousands of specialized GPUs or TPUs running continuously for weeks or months, costs ranging from millions to tens of millions of dollars. Enormous energy consumption. This is why only well-resourced organizations train the largest models from scratch. The result of pre-training is called the base model or foundation model. It's knowledgeable and capable at completing text, but it's not yet a helpful assistant. That takes some more steps. Next, scaling laws and emergent abilities. Before we move, before we move on, let's talk about two fascinating phenomena that shape how these models are built: scaling laws and emergent abilities. Scaling laws. Researchers discovered something remarkable. Model performance improves predictability as you increase three things: model size, dataset size, compute. These scaling laws are surprisingly smooth and predictable. Double your resources in the right proportions and performance improves by a predictable amount. This predictability lets teams forecast how good a model will be before spending millions to train it. The balance. Importantly, research showed that many early large models were actually undertrained. They had lots of parameters but hadn't seen enough data. The insight was to balance model size and data size together. This led to models that are smaller but trained on much more data, often outperforming bigger but undertrained predecessors. Efficiency, not just size, became the goal. Here is truly surprising part. As models scale up, they suddenly develop abilities that smaller models simply don't have. Capabilities like multi-step reasoning, translation, and solving word problems can appear rather abruptly once a model passes a certain scale. Abilities nobody explicitly programmed. These emergent abilities are one of the most intriguing aspects of LLM. It suggests that quantity, enough scale can transform into new qualities of capability. It's part of why the field has pushed toward ever larger models, though researchers are still working to fully understand exactly why and when these abilities emerge. Next, fine tuning and alignment. After pre-training, we have a base model that is great at predicting text but doesn't necessarily do what we want. If you ask it a question, it might continue with more questions instead of answering because that's a valid text completion. To turn it into a helpful, safe assistant, we need additional training. This is where fine tuning and alignment come in. Supervisor fine tuning. SFT. The first step is supervised fine tuning. Here we train the model on curated examples of desired behavior, typically high quality pairs of instructions and ideal responses. For example, thousands of examples like instruction. Explain photosynthesis simply. Ideal response is a clear, well structured explanation. By training on how many such examples, the model learns the pattern of being a helpful assistant that follows instructions. It learns to answer questions, follow formats, and respond appropriately. This is sometimes called instruction training. The alignment problem is, but we want more than just helpful. We want the model to be honest and harmless too. We want to refuse dangerous requests, avoid making things up, and align with human values and preferences. This is the alignment problem, and supervised examples alone are not enough because it is hard to write perfect examples for every situation. Reinforcement learning from human feedback. RLHF. The breakthrough technique here is reinforcement learning from human feedback, or RLHF. It works in stages. Stage 1, collect human preferences. The model generates multiple responses to prompts. Human laborers rank them. Which response is better, more helpful, or safer? This produces a data set of human preferences. Stage 2, train a reward model. Using those human rankings, we train a separate reward model that learns to predict which responses humans would prefer. Essentially, it learns to score responses the way humans would. Stage 3, optimize with reinforcement learning. Now, we fine tune the LLM using reinforcement learning, using the reward model as a guide. The LLM generates responses, the reward model scores them, and the LLM is adjusted to produce responses that score higher. Over time, it learns to generate the kind of responses humans prefer. The result, this process is what transforms a raw based model into the polished, helpful assistants we interact with. RLHF is a big part of why models became genuinely useful and pleasant to work with. The field keeps evolving. Newer techniques aim to make alignment simpler and more efficient. For example, direct preference optimization or DPO achieves similar goals to RLHF but with a simpler, more direct training process, avoiding the need for a separate reward model and reinforcement learning loop. There is also growing use of AI feedback, sometimes called constitutional AI, where an AI system helps critical and refine responses according to a set of principles, reducing reliance on human labeling for every case. Why alignment matters is alignment is arguably as important as raw capability. A powerful model that's unhelpful, dishonest, or harmful is not useful and could be dangerous. Getting alignment right is one of the central challenges of modern AI development, and it's an active area of intense research. Now, let's go to challenges and limitations. Let's be honest about the challenges and limitations of these models and their training. LLMs can generate confident sounding but false information called hallucinations. Because they are fundamentally predicting plausible text, they can produce statements that sound right but are not factual. Reducing hallucinations is a major research focus, often addressed by connecting models to external knowledge sources. Knowledge cutoff. The model only knows what was in its training data. Events after its training cutoff are unknown to it, unless it is given tools to look things up. This is why models are often paired with search or retrieval systems. Bias. Models learn from human generated data, which contains biases. Without careful mitigation, models can reflect or amplify societal biases. Addressing this requires careful data curation, evaluation, and alignment work. Compute and environmental cost. Training and running large models consumes significant energy and resources, raising cost and environment concerns. This drives research into more efficient models and training models. Lack of true understanding. There is an ongoing debate about whether these models truly understand our sophisticated pattern matches. They can make surprising errors on simple things like while excelling at complex tasks, revealing they don't reason exactly like humans. Data and privacy. Training on vast internet data raises questions about copyright, consent, and privacy. These are active legal and ethical discussions shaping now how models are built. Understanding these limitations is essential for using LLMs responsibly and for appreciating where the research still needs to go. So, what is the future? So, where things are heading, where we are heading. The field is moving towards fast toward more efficient training, doing more with less compute, multimodal models that handle text, images, audio, and video together, better reasoning through techniques that let models think step by step. Models augmented with tools, memory, and real-time knowledge retrieval, improvement, improved alignment, and safety methods. So, what are the key takeaways? Let's recap what we have learned. Language modeling is fundamentally about predicting the next token. Text is converted to numbers through tokenization and embeddings, transform architecture, pre-training teaches the model, scaling laws make performance predictable, and scale produces emergent abilities. Fine-tuning and RLHF align the model to be helpful, honest, and harmless. Real challenges remain hallucinations, bias, cost, and more. So, what is remarkable is how a simple objective predict the next word combined with scale, clever architecture, and human feedback produces systems that can write, reason, and converse. It's one of the most exciting developments in the history of computing, and we are still in the early chapters. Thank you so much for watching. If this helped you understand how LLMs learn and train, please give it a thumbs up, subscribe for more AI content, and drop your questions in the comments. Until next time, keep learning and stay curious.